Okay, this is our last note set in the first unit, which is focused on just kind of some general DSP stuff that we will use in this course on digital audio signal processing. So things that didn't fit specifically into the other units, which are more specifically targeted at digital audio. So this is called state space view of systems. I didn't state a reading for this. It's available in almost any book on signals and systems and control systems. And in fact, there are entire books dedicated to state space analysis of systems. So you should be able to find something, but we're not going to need very much of this. So probably no real need to go off and do any deep reading. So what is state space? Well, it's just yet another way to provide a mathematical model for an LTI system. And, you know, it can be modified to do nonlinear systems as well, and that's maybe one of its advantages as well. So we'll see its application in implementation of nonlinear effects later in the course. So if you looked at a typical signals and systems class, you probably learned 4 different ways to characterize a system, and they're all equivalent. And I show them on this diagram here, which is my way of thinking about how they're all interconnected. So what do we have on this diagram? We've got the difference equation over here, which has this form. This is all for discrete time. We could do something similar for continuous time. You can see a dividing line here. This is the time domain, and then this is the Z and frequency domain. So remember, Z is just a generalized version of frequency domain. So the difference equation is on the time domain side. Look, it has only time functions involved. And the way I have it written here, we can compute y of n based upon past outputs and current and past input samples. So that's a recursion. So we don't really use the difference equation for analysis. We use it for thinking about how to implement. In fact, if you write code or build FPGA hardware to implement a discrete time system, you're really just implementing the difference equation, unless you were to do it using this new thing, the state space. Impulse response, that is something down here. That's h of n, also to the left of that line, so it's a time domain thing. We generally don't use this to compute the output in an actual system, but we might lay it out to think about it. Although, having said that, we will when we try to emulate the reverb of a room. We will literally try to implement the convolution of the input signal with the room's impulse response. But it's mostly just an alternate way of thinking about the system. And these two things are related to each other, even though I don't show an arrow here between them. You can go from the difference equation to the impulse response. It's just nobody really does that. Then we have the transfer function. I kind of put that in the center here because I kind of view that as the central, most important point and viewpoint of linear time invariant systems. We have an h of z here. It's on the z side. So it's a frequency response thing. It's a frequency domain thing. And for analysis, that's pretty much what we use it for, to think about how the system is going to work. So we use multiplication between h of z and x of z to get the z transform of the output, and then do the inverse z transform to find the output. That's for all analysis. And often we don't even really do that multiplication, let alone do the inverse z transform. We might just look at h of z to see what it looks like, and that might involve the pole zero diagram. So I put that on this chart. It's not a way to model the system because it doesn't tell us everything there is to know about how to think about how the system's going to behave, but it tells us a lot. So it's you can kind of think of it as a graphical representation of the transfer function in some respect. And then we have the frequency response, which is down here also on the frequency domain side. We get it from the transfer function. We replace z by e to the j omega, and here I'm back to using capital omega as our discrete time frequency. The previous two notes were based on a book that used theta, so I used that there. Again, using multiplication to do the analysis. And again, we generally don't just look at we generally don't do that multiplication. We just look at the frequency response to see what it's going to be doing. And that's how we think about this. Those are our four views of frequency response, or of an LTI system, our four ways to model it. I also have a block diagram on here. I already talked about the pole zero diagram. Both of those are kind of graphical ways to think about the system. The block diagram is literally can be thought of as a way to implement the system. And it can be linked to the difference equation and the transfer function. So we've looked at that previously. The block diagram is kind of a nice way to think about how a system behaves and works. So what about state space? Well, we've got another model. That's just another way. And it's more common in the control systems field than it is in DSP. But if you're a DSP person, you ought to know something about it so that you can exploit it when needed. But as far as control systems go, the modern view of control systems is all based upon state space views. So here's a nice augmented picture. I've added in the state model here. I've made it yellow so that it stands out a little bit more. And I've given the expressions here. And unlike the others, you can see that it requires two parts. There's something here called the state equation, and then something called the output equation. And we can see that although one could go from impulse response to state equation, or maybe frequency response to state equation, that's not the common way to do it. It's more organically linked to difference equation, transfer function, and block diagram. In fact, as we go through this set of notes, we'll really see that the block diagram and the state model are linked together very, very nicely. Okay, so we need to understand what these two different things are. And I say down here similar for continuous time. I'm going to show continuous time stuff for the state model as well as discrete time stuff, because there will be a point in this course where we'll be talking about a particular continuous time filter that we want to convert into a discrete time version, and it's most easily done by thinking about it in terms of continuous time state space representation. Okay, so what is this state that we're talking about? What is this concept? So let's go back to your differential equations class. You were talking about nth order differential equations, and in your signals and systems class, you talked about nth order difference equations. And in both of those scenarios, you knew that you needed some initial conditions to solve this. Now, you may set those initial conditions to 0, but you still need those one way or another. And the interesting thing is that for an nth order one of these models, you need to know n initial conditions. That's almost the definition of the order of a system. Almost. It's very closely related. So you may have seen that for a difference equation, we usually, especially if we were recursively solving it, we needed to know the previous n output values before. Those are the previous ones that occurred before we start applying our input. So however it got to those doesn't really matter. And then you might also remember from your differential equations class, you needed n initial conditions, and they were usually derivatives. And the 0 minus just was the derivative right before your input started. So your input was 0 up to a point, and then it changed. So right before that change, that's what the concept of 0 minus is. So technically, from a math point of view, it's the limit from the left going to 0. But it's derivatives. It's n derivatives. The 0th derivative, the first, all the way up to the n minus 1th derivative. So those were classic initial conditions that you learned about. Now, you also have studied some systems more physically, and you learned about needing to know internal values for those systems for your initial starting point. So you may have learned that for an RLC circuit, to solve that, you needed to know the initial capacitor voltages and the initial coil current. So coil, I use that term for inductor because inductor has 3 syllables and coil has 1, and it goes nicely with cap and coil. So those were the initial conditions that we needed. And they could be related to these. In fact, if you know those and you know these, they're equivalent to each other. One can get one from the other and vice versa. And then for discrete time systems, you may have learned in a signals and systems class or maybe a DSP class that the initial conditions could also be taken to be the initial values stored in the blocks, the memory blocks, the z to the minus 1 blocks. And so those are not necessarily equal to those, but they are equivalent. So just some different ways of specifying the initial state of the system. So in fact, when I teach signals and systems, we solve the output of the system, and we break it down into 2 parts: the 0 input solution and the 0 state solution. So the 0 state solution was assuming that all the initial conditions, whatever form they may take, were assumed to be 0 for that, to get that part of the solution. So my students have seen the word state before, but not necessarily in this most general view. So the concept of state generalizes these ideas of initial conditions. So first it says, well, it doesn't have to be these, and it doesn't have to be these. There are other choices. And in fact, there are infinitely many different ways to choose the initial state of a system. So what really is that idea of a state? So here is a rough definition of the idea of the state of a system. I say rough, I guess more just kind of loose, not rough, but there's some ambiguity here because it doesn't tell you what it really is, just tells you what it needs to allow you to do. So the idea is that the state of a system at some time n0 is the smallest set of numbers that is sufficient to determine the behavior of the system for all future time, provided that the inputs to the system are also known for all those future times. That's the idea. So look, that's what these things are, right? The state at time 0 is these. If I know this at time 0, if I know these things and the input for all time 0 and into the future, I can find the output. So it doesn't have to be these initial outputs. It doesn't have to be the values initially stored in the blocks of the diagram, of the block diagram. Could be anything that allows us to do that. So that's kind of an ambiguous definition, but it sets the stage. And we're only going to focus on a few concepts here. If you read an entire book or a book that has a few chapters on state space, you'd get lots more detail as to how to nail down what the state is. But we'll get there to some specifics here in just a little bit. So, but what we can see here is that And we saw that up here. The state is not a unique choice. And so that is one of the beautiful parts of this, is that it gives us that flexibility. I can choose it this way, or I can choose it that way. And so notice that we're just also saying at some time n0. So it doesn't have to be the concept of initial. It's just at any instant of time, you stop the system, freeze it at that instant of time, and there's this thing called the state of the system at that time. That's everything you need to know to figure out how it's going to behave in the future with an input from that point forward. That's the idea. So I'm going to use, there's a lot of different notations that people use for what the state is. I'm going to use the symbol Q, and it's a vector, right? Because look, for an nth order system, I'm going to need n things, right? So it's going to be a vector. So at the instant of time n0, this will be the vector. And I use bold, non-italic, lowercase to denote a vector. And if I want to do continuous time, everywhere I've got n or n0 here gets switched to t and t0. So that's the idea. So that's the initial state, or just the state. And now we can think about that state changes with time. It starts at some initial value, and then we start applying an input that's going to change the state of the system. And remember, I said freeze it at some point. And now we can ask, what's the state of the system now at that instant? So the state is varying, it's changing. So we call those the state variables. So the state variables can be stacked into a vector. So we would have the state variable vector, which we'll just shorten to say the state vector, and it will be a function of time. We can change our focus on the system. Instead of trying to figure out how the output works, it turns out that the state is everything that we need to know about the behavior, at least the internal behavior of the system. So we look at the state vector for all time. And then what is our use of this? What's our point? The first thing that we want to ask ourselves is, for a given system and a given initial state, can we find the state vector as a function of time for all points in the future? That's the first part of this. And then the second part is, given that we've found the state vector for all time of interest, we can use that to find the output for all time. And a cool thing is that when we do this first part, we don't necessarily need to know what part of the system we're considering to be the output. So suppose you have some complicated RLC circuit. You use the state view, the state vector analysis part, to figure out how the circuit is behaving internally. And then you say, oh, and I'm really interested in the voltage across this capacitor. That will be our output. And then we can convert the found state vector into the output that we desire for all time into the future for a given input. So for analysis, we do this first. We figure out how the state's going to behave, and then we do the second task. Having done that, that's analysis. We're off trying to figure out how this system is going to behave. We're not going to do that in this course. In this course, we're interested in using the state view for the implementation of a discrete time system. So in that setting, for discrete time anyway, this doesn't really carry over to the continuous time view, but we do the first task at our current n value. So that involves taking the initial state. When we start, we've got an initial state, and we will figure out how does that state change from there to the next instant of time. And then we do the second task. We find how that new state contributes to our desired output, our chosen output position. And then we'll cycle back. So first task, then second task, then first task, then second task, as we iteratively go through the times. So in that sense, it's kind of like a generalization of the recursive solution from the difference equation. Okay, so we've been dancing around what this state space model is. So let's take a look. We've already seen that it needs two parts. One that tells us how to find the state vector's values at a given instant of time, and then a second one to take that state vector's value at that time and compute the output. Oh, vector. So this is nice. We could handle multiple outputs all at once if we want. So maybe we have a system and we're saying, a circuit, and I want to know 3 voltages from that circuit. This capacitor voltage, that resistor voltage, and maybe that inductor's current. And it doesn't have to be currents with inductors and voltages with capacitors. Any current or voltage in the circuit anywhere can be specified as an output. So for the discrete time version, they look like this. Here is Q of n, that's the state at time n, and here's the input at time n, and those things get multiplied by appropriate matrices to compute the next state vector. And then once I have a state vector, so suppose I know the state vector at time n, and I know the input at time n, I can compute what the output is at time n. So we usually write these in this direction, but if we think about what we would do to iterate this, we usually start here and say, I know what the initial state is, so I can find the initial output. Now I take that initial state and I update it, and now I take this and put it in here, and I take the new sample of the input, and I can find y at the new point, and I just keep going. So we just cycle through these things as we go. So that's the idea. The continuous time form is a little bit different because it's a differential equation, so we can't really think about iteratively solving it, and we won't really get too much into continuous time state space models, other than we'll say, oh, here's a classic historical filter based upon some op amps, and we can identify the state form for that, and then we can convert it into a discrete time. So that's what we're going to do in this course. But in a continuous time control systems course, you would use this to analyze how that system's going to behave, just like you would use transfer function or frequency response or impulse response. So there's our models. Note that in each case, we have two parts, a state equation and an output equation. And then down here, I just give some names and some sizes of these things. So A is usually called the system matrix, although for discrete time, it's also called the state transition matrix. So you may hear me refer to it as that, because it tells us for discrete time how the state transitions to the next state. Continuous time, it doesn't quite work that way. So either system matrix for both, or discrete time, it could be system matrix or discrete or state transition matrix. And if we're talking about an nth order system, A is going to be an n by n matrix, and the state is an n by 1 vector. So that makes sense. And then B, well, we could have an input vector. So that's nice, handles multiple inputs. So in audio, we might have stereo. So R could be 2, in which case B needs to be an n by 2 matrix. But in general, n by R, called the input matrix. And likewise, we could have multiple outputs. That's nice. So in a stereo input and stereo output, R and S would both be 2. So C is the output matrix, and then D is called the feed-through matrix. There might be some other names for that, but it's basically saying that X can directly contribute to the output in addition to the state. So notice that the state has some contributions from the input, but then the input can also directly be coupled to the output. So this is sometimes called the direct matrix, I think, but I like to think of it as the feed-through matrix. So note what we've done. We've taken an nth order system, which would be described with an nth order diff equation, differential or difference, depending on which one you're talking about, into what looks like a first order system, but it's a bunch of, it's n different first order diff equations, and they're coupled because A can couple one part of the system or one part of the state vector into other parts of the state vector. So that is kind of the big idea here. We're replacing a single nth order differential equation or diff equation into n coupled first order diff equations. That is a big idea there. Okay. We've already talked about the fact that the state itself is non-unique. So I just want to talk about that a little bit more. We've already said that, for an nth order RLC circuit, we could use the initial capacitor voltages and inductor currents, or we could just use, if we've specified a particular output, we could use it's 0 through n-1 derivatives just before the input gets applied. Okay. So since the state vector is not unique, how we choose it is not unique, the way those vectors get updated will have to be different for each choice. So that means these matrices will change. So every time we choose a different set of variables for our state variables, we'll get a slightly different form of the A, B, C, and D. Now that seems confusing, but it's actually powerful because there are some scenarios where one form is desirable and other scenarios where another form is desirable, and that's kind of part of the charm and power of the state space view. For our use, we're just really going to focus on one form, and I'll show you that in just a little bit. So even just changing the order, so here there's an obvious order for those, but for the cap voltages and inductor currents, what if I put those in one way, all the cap voltages and then all the inductor currents? Maybe I switch those around. Well, all that's really going to do is create permutations of these matrices, but still it's effectively a different state space model. But all of these models for the given system will give us the same answers, but just sometimes might be more illuminating as to how it's working inside. All right. So it's convenient to introduce this thing called operator form. And again, there's no fixed symbol here. So let's start with discrete time. We're going to define something called the advance operator. So if I take something at Q of n and I hit it with this operator, it's going to bump it ahead one sample. That's it. So instead of writing Q of n plus 1, I could write EQ of n. So that's the idea. That's the advance operator. So then I can rewrite my state equation. So this hasn't changed, but right here, instead of writing Q of n plus 1, I just write EQ of n. Now you might wonder, what's the beauty of this? You'll see as we go through the subsequent slides here how we exploit this little idea. And for continuous time, it's easy enough to use the dot for derivatives, but we'll also find it very useful to use a derivative operator. So P operating on Q of t gives us the derivative of that. yeah, we could just think of that as DDT, but it's just a simplified notation. So that's kind of the idea. And we just think of it as multiplying it, this operator that hits that and creates the derivative. So that's kind of interesting. And so now we can rewrite the continuous time case this way. Again, this has not changed, but here's the big change. Okay, now one of the advantages, and this is just purely notational, is that we can drop all of the time indices, just make it a little easier to write things out. It's just convenient. So instead of writing of n, of n, of n, we just drop all that. And instead of writing of t and of t, we drop all that. So just a convenient little way to write it. That's all. Nothing more than convenient notation. Yes, I was wondering if I needed to say something else, but I think I say it later. So let's talk about the connection between the state model and the block diagram. I said earlier that really, in principle, we can get the state model from any of the other representations of the system. But I said there were three that were most common. For discrete time, it would be the difference equation, the transfer function, and the block diagram. So to go to continuous time, just change difference to diff. Same thing for continuous time. But the block diagram has a very nice connection to the state model that makes it very easy, at least for what our purposes are, makes it very convenient and easy to think about it that way. So now also keep in mind that just like state model, there is no unique state model. There's also no unique block diagram. And you may have seen this in a DSP class or maybe in your signals and systems class, but maybe not. But there are many different ways that I can write a block diagram for a nth order diff equation. And so some of those I list here, and maybe you've seen those, but it's not important that you have that under your belt, so to speak, for this course. But just keep that in mind. So each of these different block diagrams leads to a different state model. So that's kind of nice. We're seeing that there is a connection between the state model, so the structure of the A, B, C, and D matrices, as well as how we define the elements of the Q matrix, has a connection to how we draw out a block diagram. So let's take a look at this for the continuous times case. And I'm going to do a third order system. And notice that I have the same order on both sides. Doesn't have to be true, but what's important is that I have a third order derivative over there. That's what makes this a third order system. So if you remember from signals and systems, we can write this as a block diagram. And maybe you didn't see that. Maybe you saw it in a control systems course. But if you didn't see it, trust me, this is how you would do it. And I'm doing it in terms of the P operator. So if you were thinking in terms of signals and systems or control systems, you would think of a 1 over S there. And from your control systems background, you might know that that 1 over S is an integrator. So more on that later as we use these later in the course. But for right now, we can convince ourselves that this will allow us to model this differential equation. And pay attention to the ordering of the coefficients, 0 to 2, 0 to 2, and a 1 out in front, and then 0 to 3 here. So the order of those in the differential equation impacts the order that they go in the block diagram. So this is a fairly standard form for the block diagram. It has a name, and we'll allude to that later. Now the P is the derivative operator, so 1 over P is like an integration operator. So we think about the output here is the integral of whatever's going in. So again, if you've taken control systems, you might know that the 1 over S box is viewed as an integrator. So we can think of P here as equivalent to S, if that makes you feel more comfortable. Although technically, if we're talking about putting S there, we should be putting X of S and Y of S here. The P is more thinking like it's an operator applied to a time domain function that does those. But those are subtle things. So here's the deal. If we have a block diagram, whatever form it is, the simplest way to specify the state variables is to pick the state variables as the outputs of the integrator boxes. So every form of continuous time block diagram is going to have a whole bunch of these integrator boxes, and however many it has, that's the order of the system. So for a third order system, I've got 3 integrator boxes. So I'm labeling the outputs of those as the state variables. And I write them as functions of time. And then I can group them into a vector, Q1 at the top, Q3 at the bottom. Now, I could just as easily made this Q1 and this Q3. I could name them or number them arbitrarily in a lot of different ways. That's going to change the form of the matrices, but not really change the nature of the system. So this is the canonical way to do it. Start back here and move this way. So that's the idea. So now we have our state variables defined, and now we can write relationships. So if we look at this, remember I said this is the integral of this. Or in other words, Q1 is equal to Q2 times 1 over P. So Q1 is equal to 1 over P Q2. And here's the beauty of this operator view. We can think about that as just something that we can swing around almost as if it's a variable. It's not, but it will behave like that. So we can swing that over in the front. And now we see PQ1 is equal to Q2. So that describes what's happening here. It's a relationship between those two state variables. And then same thing here. PQ2 is equal to Q3. And then we get to here. So here's the idea. We're writing equations for everything that is an input to an integrator box. So first step is state variables are the outputs of the integrator boxes. Then write an equation for each input to an integrator box. So those two were easy. This one's a little harder. So that's going to be PQ3. So that's just essentially the name of that box or the input to that box. And what's going in? Well, X is going in. And what is this? Minus A0 times Q1. And what is this? Minus A1 times Q2. And what is this? Minus A2 times Q3. So we've got all of those. So there are the state relationships. And now look, this is the operator, the derivative operator. So that's the vector that's going to be on the left side of my state equation, and this tells me what's on the right side of it. So now I just write it out in matrix vector form. So here is my Q of t. I don't show it here, but it would be Q1 on top, Q3 on the bottom. So what do we get? Right? We get PQ1 at the top here is equal to 1 times the middle one. So 1 times Q2, and so on. And then this equation here is captured by Q folding over those and creating the third element of that, plus X of t. There it is. Okay, so there's our state equation. That was simple, from block diagram to state equation. And where did this block diagram come from? Well, it's the standard form that you may have learned somewhere. And now we can write the output equation. So in this system, we're specifying a single output. We have a single input, in this case 2. We could have multiple inputs and multiple outputs, but in this case, what is the output? Well, it consists of B0 times Q1, so that goes here, B1 times Q2, B2 times Q3, and then B3 times all of this stuff. Well, that was this, right? So that all goes in there. Now we need to just modify that and get it into a nicer form. So there's what we just had on the previous slide. And now I've just grouped all the Q1 terms, all the Q2 terms, all the Q3 terms, and the X term. And we see a nice little structure here. So once you have the block diagram, you can almost by inspection write down what we have for that. So there's our output equation. So we can write that in matrix form. In this case, since we have a one and only one output, this C matrix is a 1 by 3. And D, since we have a one single input and a single output, that's actually a scalar 1 by 1. So we've gone from difference equation to block diagram to state model. And there's a clear structure here. And we can easily generalize this to other system orders. So if you were to see any ordered differential equation, you could write this form of state model. And this is a particular special form. This is what's called a canonical form. There's several canonical forms. You don't know what that word means, just look it up in the dictionary. The dictionary definition is exactly what we mean that to be. And if you have taken a controls course, this is what's known as the controllable canonical form. The other big canonical form is called observable canonical form, but there are some other ones as well. But this one is the only one we'll care about, controllable canonical form. Now, there are MATLAB commands that you put in the parameters, the coefficients from a diff equation, whether it's continuous time or discrete time, and it claims it will give you a state model. But what state model? Remember, there's no unique state model. So if somebody said, I have a command that will take this and give you a state model, you should ask yourself, what state model? Turns out it's not the controllable canonical form. I think it's the observable canonical form that it gives. So beware. Don't use this MATLAB command to get the controllable canonical form that we're going to be using in this course. All right, that was continuous time. Here's discrete time. Here's a third order system. Again, I don't necessarily need to go all the way to 3, or I could go past 3 over there. What's important is that the distance between the most advanced and the least advanced term on the left is 3. And that is what sets the order of the system. So here is the standard block diagram for that. So again, you may not know where this comes from. In my signals and systems class, I just kind of show it and say, this is it. In my DSP class, we developed this from first principles. This is called the direct form 2. We start with the direct form 1 and then convert it into this direct form 2. So that's where this comes from, but you may be familiar with it. But I've written it here in terms of E. E is the advance operator, so 1 over E is the delay operator. See, P was the differentiation operator, and 1 over P was the integration operator. Same kind of idea. They undo each other. Like I said, we can think of E as equivalent to Z. Remember, Z, multiplication by Z in the Z domain corresponds to advancing, and multiplying by Z inverse, or 1 over Z, corresponds to a unit delay operation. So same idea. And just like before, we're going to take our state variables as the outputs of the delay boxes. Just one choice. There are other choices, but this is the choice that we will be making for our needs in this course. And again, we start at the rightmost side and work up that same way as we did before. And just like we did for continuous time, we're now going to write, well, I don't do it, but one could write the equations for the inputs to those delay boxes and then manipulate it into the form needed for the state model. So if one were to do that, you would get something that looks like this. Now, be aware, the way I laid out those coefficients are different for the discrete time versus the continuous time, the way I numbered them. So just be careful. But similar, very similar kind of thing. We get the same kind of structure here. And again, this is the controllable canonical form. And like I said, MATLAB will give you something different. So if you take the numerator and denominator coefficient vectors, like you would normally put into like freq z or something like that, and you run the transfer function to state space, it will give you some matrices, but they won't be the canonical controllable canonical form. Gives you the observable canonical form. Now there may be another command that allows you, or a way to call this to give the controllable canonical form. I don't really know. I don't use this command on a regular basis. Also, just a warning, this comes right from the MATLAB help function on TF2SS. When you're calling it for the discrete time case, you have to be a little fussy about appending some zeros on the end of one of them to make them the same size. So keep that in mind. But again, gives you the wrong form, so I wouldn't encourage you to use it in this course. Okay, we're almost done here. Once we have the state model, sometimes it's useful to go back to the transfer function. So the state model allows us to do things and see things, but the transfer function also allows us to do things and see things. And so it's just, state space is just another model, and it's useful to have as many different models and be able to use them all at the same time in your brain to see what's going on with the system. So we can generalize the concept of transfer function from single input to single output to multiple input to multiple output. But I'm just going to focus on single in, single out. But the ideas carry over. So here's the idea. We're going to take our state equation, and when we're talking about transfer function, it's always under the scenario of zero initial conditions. That's the definition of transfer function. Comes from impulse response. The impulse response is what happens when what comes out of the system when you put a delta function in and the system is in zero state condition, zero initial conditions. So if you take the Z transform of the given discrete time state model, and under this assumption, you'll get just that there. Without that assumption, you'll get some additional terms that have the initial conditions involved, but we don't want those because we're trying to find the transfer function. So look, remember that was E times Q of N. Now we get Z times Q of Z, and everything else just transforms, straightforwardly. So now we have our state equation and our output equation, but in the Z domain. So it's kind of a mixed model at this point. But now we can algebraically solve. We've got a Q of Z and we've got a Q of Z, and we can manipulate. Z is just a variable, so we can solve for Q of Z, and we end up getting this matrix that gets inverted. And that's an important matrix that plays a lot of important roles when you're analyzing discrete time systems using state space models. But for our purposes, we're not really going to worry too much about it. But we can identify now, if we take this thing and plug it into there, now we're going to have an X of Z and an X of Z and factor out the X of Z, and we get something. And if you look at this carefully, this is one by one, and this is 1 by 1. So this has to be a scalar, 1 by 1, a scalar that is a function of Z. So that's true when we have single input, single output. And so it is the thing that multiplies the input to give the output. So it is the transfer function. So now we have a result. So if you have any one of the many possible, infinitely many possible state models, you've got your A, B, C, and D, you can plug them in here and find out the transfer function. So it's a nice passage back and forth between those. And if we did a similar thing for the continuous time case, we would get this similar result. So virtually identical except Z and S. That's it. And now in this case, MATLAB command SS2TF will do this for you. And there's no real gotcha here because you're starting with a specific state model. So unlike going the other direction, you don't know what form it's going to give you, and it might not be what you want. Well, it gives you the observable canonical form, I think. But here, you start with your specific form for the state model, and you get the transfer function. So that's a convenient thing, especially given that finding that inverse can be a little bit challenging. Okay, we're not going to do that too much, but we will occasionally see that. And I just threw that in just for completeness. And I also threw this in for completeness. This is how we might use a state model to analyze a system. That's not what we're going to focus on here. But it involves that inverse matrix that we just saw, and it involves eigenvalues of the matrix A. Hey, look at this. That, if you remember eigenvalues, that's the kind of thing that you see showing up in the definition, not the definition, but the characterization of eigenvalues. So that's no surprise. So a lot of the system analysis based upon the state model boils down to thinking about eigenvalues of the matrix A, and to a lesser extent, the eigenvectors of the matrix A. So it opens up a whole range of mathematical tools to think about how a system's going to behave. Now, we're not going to do that. I just threw it in for completeness. What we're going to do is start with a continuous time state model for a filter, and then we will convert it into an equivalent discrete time state model, and then we'll use that to implement that filter. And it'll be really nice. So it's just a convenient form to recursively implement the discrete time system. A little differently than recursively solving the difference equation, which would be equivalent, but this is just a nicer, easier way to do it. So remember, this was our discrete time state equation and output equation. And I say do the first task at current end, then do the second task. But as I said before, we really want to start with the second task, because we're going to start with Q of 0, which will allow us to get Y of 0. We would put in a 0 here. Then we're going to put in a 0 here and a 0 here. So we start with our initial state vector, and then that updates it to Q of 1. Okay, now I've got Q of 1, and I'm going to plug that in here to compute the output. So now I've got 1 and 1, and I can compute that. And now I've got 1, I plug it in here, 1 and 1, and I get 2, and so on and so on. So we really start with the second task first, and then update the state, and then output, then update state and output, update state and output, and so on and so on. So that's how we'll actually implement some interesting things in this course later on.